All right, so really cool, kind of a cool topic today. Different than anything we've done all year in a way. So we're going to look at some new kinds of functions, piecewise functions. How familiar are you with piecewise functions? Maybe none at all. Maybe have you even heard the term piecewise function before? Okay, I wouldn't think so. That's fine. That's fine. So there are different kind of function that we use to represent very specific situations. And if we're applying math to some kind of a real world situation, oftentimes these are useful to us. But they're different kinds of situations. This would be a more typical application of math. Like if we wanted to find out the downrange or the range of a projectile that we're going to launch out of a cannon or something. That's a pretty straightforward application of math. It just uses some functions we can build to make that prediction. Let's look at a couple quick examples here, something like that. Okay, so it's kind of a fun little thing to mess around with. Here's a simulation that relies on math to make predictions. So we've got this cannon. We can control the height at which we shoot the cannonball. We can control the angle of elevation of the cannon. There's 0 if we're shooting it horizontally. 90 degrees would be straight up. That's probably not a good idea. Or somewhere in between. And we can control the speed in meters per second. We can pick anything between, say, 0 and 30. So why don't I'm going to put this thing out here at, I don't know, let's put it out about 40 meters. Let's see if we can hit this target. Anybody want to take I'm going to go ahead and set the height of this thing at, 10 meters, how about? Anybody want to take a stab at an angle and a speed that's going to hit the bullseye? You want to take a guess? What do you think? Okay, 20 meters per second, and we'll say 20 degrees. Okay, try that. See how we did. Ooh, that's pretty close. Okay, we got to adjust things a little bit. What do you think? What's an adjustment we could make here? Okay, maybe 19 meters per second, something like that. Oh, 19 did it. Okay, and we could pick some different angles, and that was good. And based on the angle, we're going to get some different values, right? Okay, so again, how is this simulation predicting where the cannonball is going to land? Just math, right? It's just math. That's all it is. Here's another, I just threw something together here to kind of show you what that might look like if you were looking behind the scenes at something like this. Here's what the math would look like if we were trying to, make a prediction of range as a function of what are the parameters here? The height of the pedestal, the height from which we're launching our cannonballs, the angle, and the speed. So if we pick a height of 10, an angle of 45, and a speed of 50, for example, that's what the trajectory would look like. We're graphing the height as a function of downrange distance, and so notice it starts off at 10, right? When it hasn't traveled downrange at all. Its highest point would be a height of about just under 74 meters, and that's going to be downrange like 127.5-ish meters. And it hits at 264.7-ish, right? So just shy of 265 meters is where that thing would land, right? And just by changing the values, what's kind of nice about Desmos is we can change these parameters. The guy could change the height, and it's going to impact what that math model predicts, right? And if I change the angle, again, it has an impact on where the thing is going to land. Change the speed, has a big impact on where it's going to land, okay? So that's just kind of behind the scenes. That's what you would see for the math model based on that function that we built. Okay, what that didn't really take into account, though, is, whoops, I gotta go back. What did I not take into account with either one of those models? It actually wouldn't depend on the weight of the cannonball at all, but there is something that would impact the trajectory that we didn't really take into account. Again, here's, air resistance. Air resistance might have an impact also, right? So let's look at a prediction with air resistance. Okay, let's take something like an initial velocity of, initial velocity of how about 100 meters per second and a launch angle of 45 degrees. And let's see what that would predict for our downrange. Yeah, it goes far. Goes out there about 1,020 meters, over a kilometer if we launch this thing at 100 meters per second, which would be something, what would that be in terms of, that'd be something like, 60, a little more than 62, let's see, that'd be, like it'd be something like 100 meters per second would be like feet per second. So that'd be something like roughly 330 feet per second. That's pretty fast, right? Get pretty fast. Well, what do you think if we include air resistance that's going to look like? Let's take an example of like a golf ball. So a golf ball has a coefficient of drag about 0.09. So let me drag this out to 0.09. So what's our model's prediction of how far a golf ball would go in the air if we hit it with 100 meter per second initial velocity at 45-degree angle? What do you think?
850.
It's how much? 850? Probably pretty far, but not quite as far. Not far at all. Look at that. Yeah, so turns out that air resistance had a pretty big impact on what our model predicts. That's a much more sophisticated model to take into account air resistance. That's well beyond the first one I showed you. That would involve some differential equations, second order differential effects, and that's going to be a pretty tough undergraduate level calculus problem or differential equations problem to do that one. That's a little more involved math, but if you know the math, it's not that big a deal. Okay, so let's look at a different kind of situation now. So we looked at an example of projectile motion. Let's look at a very different kind of situation. The projectile motion problem was really just one continuous story, right? The cannonball is launched out of the tube and then it's in the air and it lands. There's really only one chapter in that story. Let's look at one that has more chapters though. What if imagine the following experience. While visiting the beach at sea level, you hitch a ride on a hot air balloon that rises vertically to an altitude of 15,000 feet, at which point you bail over the side of the basket with a parachute. You plunge downward until you reach an altitude of 3,000 feet where you deploy your parachute and then you just kind of drift to the ground. Okay, sounds like fun. So what would the first chapter of our experience be, do you suppose? Okay, the rise up to our 15,000 foot altitude. And we'll assume we do that at constant speed, right? Okay, so that's, who knows, roughly an hour maybe that takes, okay? Nice tranquil ride up to our 15,000 feet. What's chapter 2? Okay, you bail over the side. So when does chapter 2 start? When you bail over the side. And when does it end? Let's see, okay, I'm going to claim that chapter 2's got to be a little shorter than that. Think about what would happen when you bailed over the side of the basket. What would you experience? Okay, you're gonna feel it in your stomach. You're gonna accelerate downward. Do you accelerate forever? Okay, what happens? Okay, you hit terminal velocity. How does that work?
Force of gravity balance the air resistance.
Okay, good. Yeah, so when you first jump over the side, how many forces are acting on you? Just one at first, right? When we're at rest and we jump over the side, there's really only one force acting. That's gravity pulling us down. But as we pick up speed, what happens? Air resistance pushes us in which direction? Pushes against us, pushes us up. Gravity pulls us down, air resistance pushes us up. The faster we go, the greater the air resistance, and so eventually what happens? Okay, so eventually we go fast enough that the air resistance exactly counteracts gravity, and that's called terminal velocity. And then we're just going to fall at the same velocity, until we do something else, right? So the next chapter is really probably just the part where we're going to bail over the side and we accelerate downward until we reach terminal velocity, which roughly, let's just say that's probably going to work out to be on average about 12 seconds. Probably we fall about 1,500 feet, okay? Then what? Well, what's next? Well, not quite. When we hit terminal velocity, we got to go down for quite a while at terminal velocity. We've got to go all the way down to an altitude of 3,000 feet at terminal velocity, right? And what would that be? Well, you can change it. If you dive, that reduces your drag a little bit and your terminal velocity goes up. It'd be about 180 miles per hour. If you're kind of laid out flat as you fall, like most people do, it's about 120. That's going to take, I don't know, about a minute. About a minute you get to fall in free fall at terminal velocity. And then what?
Pull the parachute.
Yeah, you pull the parachute. Yeah, you pull the ripcord. And what's going to happen when you pull the ripcord? Describe that. Say it again. Yeah, and what's that going to feel like? Oh, man, you're going to get jerked upward. You're going to feel that your harness is going to pull really violently on you, right? I mean, you're going to get jerked upward. There's all of a sudden, how come that happens? Why is there this extra force upward when you deploy your parachute? Okay, way more air resistance in that parachute, right? And so that creates this massive upward force that's actually going to accelerate you upward until you slow down to your new terminal velocity, which is a lot slower. That's the whole point of a parachute, is to reduce your terminal velocity, right? So you get jerked upward for about 3 seconds, and then it rapidly slows your descent, and then you settle into your much, much slower terminal velocity, and you just drift to the ground, and that would take about 2 minutes-ish to get to the ground. And that's our story. So how many chapters? 5. Okay, those are very, very different chapters too, aren't they? Right? So that's going to be tough. How could we manage to come up with a single function that's going to take care of describe all 5 chapters? That's the topic of the day. It's a different kind of function. It is called a piecewise function. A piecewise function is really just a function that's made up of 2 or more functions, pieces we could call them, each with its own domain. Okay? So if we were to look at this story, if we wanted to try to graph this thing, it would look like, graph it in the XY plane. Well, we probably wouldn't use X and Y. The input variable always goes on the horizontal axis. Instead of X this time, what do you think the input variable is going to be for this function?
15.
Well, the output is probably going to be elevation, right, or altitude. What's the input? What's changing as the story progresses here? Time is, yeah. The input variable would be time, measured in whatever we want to measure it in, right? T is a function of minutes or something, who knows. And the output variable is going to be, we'll call it Y, or altitude, in meters. If we broke this into pieces, I'm not going to try to draw these to scale because it can be pretty, if the first part of our chapter takes an hour and there are parts that only take 3 seconds, that's going to be pretty hard to represent them all in the same function. So I'm just going to kind of just give you a basic idea of the shape. We start off at 0, we increase at constant speed. Here, let me go. I'll make this more like increase slowly at constant speed until we get up to our altitude of 15,000. It was feet, wasn't it? Not meters. That'd be pretty high. 15,000 feet. Then we bailed over the side, and that was green. What color was that? That was green. What's that going to look like? Well, we start off at rest, but then we pick up speed in a hurry, right? So there's the green chapter, pretty short. Next chapter is the blue chapter, where we fall at terminal velocity. So whatever that green curve, the steepness that it ended up on when it got to terminal velocity, that's what we keep for the downward plunge at terminal velocity. And that goes all the way down to about 3,000 feet. And then we pulled our ripcord, right? And when we pull our ripcord, what's going to happen? Well, now our speed's going to suddenly change. It's going to change from being pretty steep to not very steep because the wind resistance or air resistance decreases. And then the last part, we just drift comfortably down to the ground until we get to zero. Anybody see that? As time progresses, we get these 5 different things going on, right? How do we separate them? Because each of them has their own set of values of t that apply, their own domains, right? The red domain for the red part of the function would just be everything up from 0 up to 1 hour. Over that interval, we're graphing the red function. Okay? What happens then? Well, we get this green part of the domain that occurs for the next, what would we say it was? I can't remember what we said it was, like 12 seconds or something. I can't remember. What did we say? How long did it take to reach terminal velocity? 12 seconds. So we get this little green part of the domain that's like 12 seconds long. Then we get this blue part of the domain where we're falling at terminal velocity. I think we said that was like, like a minute, but I can't remember. It doesn't really matter. You get the idea, right? So this thing, oh well. Blue domain's about a minute. And then 3 seconds was the upward jerk from the parachute, right? So we get this other little piece of our domain, this other little collection set of x values that apply, or t values that apply there. And then all the rest of it is the gentle descent in our parachute, okay? Does that make sense? Get the idea? Do you see the need for a different kind of function like this, a piecewise function that has really different personalities depending on what our input value is? Sometimes functions do that. Sometimes they completely change personalities over the course of the input values, the set of input values, or the overall domain. We have to break them up into individual domains. Here's an example. Now, notice what this looks like. A piecewise function, this is how we write them. We use function notation, so like f of x in this case is equal to, and then you get this big spaced out open script bracket. There's only one. There's not another one on the right. There's only one on the left. When you see that kind of notation, that's telling you piecewise function. And then we're just going to assign 1 row for each piece of our piecewise function. So how many pieces are in this piecewise function? 3. Yeah, 3 pieces. What if I wanted to evaluate this function? What if I wanted to know what is f of 3? What's my input value? 3. Right, 3's the input. Okay, which piece would I be interested in if my input is 3? Red, blue, or green? Green. Okay, well look at these pieces here. The first piece says f of x is equal to 2x when x is less than or equal to negative 2. It would be blue, wouldn't it? F of x is equal to the function negative 1 minus x when x is greater than negative 2 and less than 4. X is equal to the function negative 3, y equals negative 3 when x is greater than or equal to 4. So we'd be using the blue piece of the function, wouldn't we, if we wanted to evaluate this? It would have to go into that blue part right there. And we would just get negative 1 minus 3. And what would our output be? Negative 4. See how that works? So we have to be careful with the piecewise function. When we're inputting a value, we have to see which part of the domain applies. You know, which piece do we plug that input value into? In this case, it'd be the middle piece. Okay, so now how could we graph this thing? Let's focus on, first step is how could we graph a piecewise function? So to graph a piecewise function, we've got to break it up into 3 different parts, right? The first step is really maybe just to think about how could we break up the x values, break up our domain into the 3 different subdomains, the domain of the red piece, the domain of the blue piece, and the domain of the green piece. The domain of the red piece is all values of x less than or equal to negative 2. Well, here's our x-axis, right? Here is x equals negative 2. So we'd only be graphing the red piece using values at negative 2 or to the left of negative 2. Everybody see that? So one thing is useful to maybe do is to just introduce some boundaries, just some vertical boundary lines that are not part of the function, but they're just there to help us organize our graph. We've got these boundaries at x equals negative 2. So if I put a vertical line at x equals negative 2, does everybody see that the red function is only going to be graphed in the region to the left of that boundary line where x is less than or equal to negative 2? Does that make sense? Okay. The blue region is going to get, or the blue part's going to get graphed between negative 2 and 4, so that's going to become our blue region in the middle. And the green part would only be graphed for values of x greater than 4, so that's going to be in the region to the right of x equals 4. Okay? All right, so in the red domain over here, we're just graphing the red piece, which is just the equation y equals 2x. Okay, that's an easy equation to graph. What is that? What kind of equation is that? What's this graph going to look like? Is it going to be a parabola or a line, or what do we got here? It's just a line, isn't it? That's in slope-intercept form, isn't it? What's the slope of our line? That's in slope-intercept form. Y equals 2x, mx plus b form. What's our slope? 2, right? Because that's the coefficient of x. What's our y-intercept? 0, because there is, if we compare this to y equals mx plus b, well, b would have to be 0, wouldn't it? Okay. So we know that if I wanted to graph this thing, normally what I would do is I would just go to the y-axis at 0, and then I would create a slope triangle to go up to and over 1 to create a second point to graph this line. But what's wrong with that approach? What's inconvenient about that? You see any practical issues with that? If I use these points to graph my red piece, they're not in the red domain. That's kind of inconvenient, isn't it? So I guess what you could do is like put those points on graph paper and then use a straight edge and only start graphing it when you get into the red region. But that's a little bit inconvenient, right? So maybe we don't want to use those 2 points. What could we do instead? Where might we want to pick our 2 points? And how many points does it take to graph a line, by the way? 2. We just need 2. So where would I want to choose my 2 values of x to use for my points? Not over here. I want them to be in the red domain, don't I? Agreed? So the easiest way to graph ordered pairs is using a t-table. This is a valuable tool, real simple, valuable tool in math. You guys know about t-tables? Have you used t-tables before? Why is it a t-table? Because it's going to look like a t when I create the horizontal line and the vertical line that creates the columns and the headers. All it is I'm just going to have a vertical column with my input values, and next to that on the right, another vertical column with the corresponding output values. We just choose values of x to input into our equation, plug those in, and calculate the corresponding y values. That's it. Okay, we could pick any 2 points in the red region, but let's be really strategic about this. What would be one x value we would definitely want to use probably in the red region? Negative 2 would be a great choice because we want to know when the red piece reaches the boundary, where does it stop? That's going to be a valuable point, valuable thing to know, right? So we're going to pick the value negative 2. Well, if I plug negative 2 in for x, what is y equal to? Negative 4. There you go. Okay, so 1 point is at negative 2, negative 4. And when you use a t-table, notice that when you read across the t-table, those are just ordered pairs. Those are the coordinates of points. And so I'm going to put a point at negative 2, negative 4 on the right edge of the red domain, the red region or the red domain. What kind of endpoint? It is an endpoint, right? Because that's negative 2 is the edge of the red region or the red domain. What kind of endpoint am I going to put on the red piece of that function at negative 2? Open or closed? Closed. How come? Okay, because the red domain includes negative 2, right? So if an ant were walking on this function and standing on x equals -2, he would be in the red part of the graph, wouldn't he, right? Okay, so we're going to grab a red solid endpoint, and that goes at -2, -4. I need one more. What's another x value I could pick? I need 2 points in the red region to graph this line. -3, sure, or what's another one? -4 or -5, just whatever's convenient. What if we just pick -4 arbitrarily? It doesn't really matter. If we pick -4, then we get the ordered pair -4, -8. So I'm going to put obviously a solid point, right, because that's a point that's on the line at, at -4, -8, puts us right there. And then how would I connect those? Hey, Brianna. Yeah, I will do. Okay, bye. Getting picked up. You know about that? Yeah, okay. Oh, I did? Oh, you're right, I did. Whoops. Should be there, shouldn't it? Okay, and how would I connect those? Would the line go forever to the right? No, it's going to stop at -2, but it's going to go forever to the left, isn't it? So the first part of the graph is just going to look like that. Agreed? There's the red piece. It's this ray that has this endpoint. It goes forever to the left with a slope, pretty steep slope. The slope is 2. Okay, give me thumbs on that. Does that make sense? Okay, what's next? We did the red part, so now what's next? Blue part, yeah. The blue part is going to exist between -2 and 4. So that's going to be our blue domain. That's the blue region where we're going to graph the blue piece of the piecewise function. Okay, that blue piece. What's the blue piece? Well, it's the line y equals -1 minus x. Is that linear? Could it be written in the form mx plus b? Couldn't it? Y equals -x minus 1 if I flip the terms around. What's the slope? -1. What's the y-intercept? -1. Okay, so it would just be a point. If I were just going to graph that thing normally, I would have a y-intercept at -1, and I'd make a slope triangle that rises by -1 and runs by 1, and that would be my line. That's fine. Sort of, that would work. What would probably be the 2 best points I could pick to create the blue linear portion of my piecewise function? Keeping in mind, I really kind of want to know where the blue piece starts and where it stops. So what x values would probably be the most convenient ones to use? -2 would be a good one. So if I plug -2 into the blue piece of the function, I'm going to get -1 minus -2. What's that going to give me? -1 minus -2. So again, if I plug in I'll use this version, -1 minus -2. That's -1 plus 2, so what do I get? 1, okay. So 1 point is going to be at -2, +1. At x equals -2, that's going to be a blue endpoint. Is it going to be solid or open? Closed or open? It's going to be open, right? Because the blue domain really doesn't actually include -2. It's just everything up to but not including -2, right? So we're going to use an open endpoint at -2, +1. Okay, so -2, whoops, I got to scoot up a little bit, don't I? -2, +1. And what would my other point I'd probably want to use strategically be? Yeah, 4. Let's use the right edge of the blue region. If I plug 4 in, -1 minus 4, isn't that just -5? So we get the other endpoint is at 4, -5. Open or closed? Open, because the red or the blue domain does not include 4, right? So we say positive 4, negative 5. We got another one. Positive 4, negative 5 right there. And then I would just connect those endpoints, and I'd get something like that. Good? Make sense? Okay. And then finally, now I've got the green region I've got to do. That's everything greater than or equal to 4. This is a pretty easy piece to graph, right? The green equation is just y equals negative 3. What's that look like? That's a line. Show me with your arm what y equals negative 3 looks like. Yeah, it's just a horizontal line where all the y coordinates are negative 3. So do you even really need to pick points this time? You know, probably not. But we will, just so we're consistent with the way we've been doing this. We could pick, like, if x is 4, y is negative 3. If x is 8, y is negative 3. If x is a billion, y is negative 3. It's always negative 3. So we just create we would just have two closed points there, right? Because the endpoint is included in the green region. So it's a closed endpoint, two horizontally aligned points, and we just start at x equals 4 and go to the right forever. So there's our picture. Okay, good. All right, so now, what is the domain of this piecewise function? We want all the values of x that an ant could possibly stand on in any of the three pieces. Are there any values of x the ant couldn't stand on? No, isn't the function defined for all values of x? Agreed? When x is less than negative 2, the ant's walking on the red piece. When he gets to negative 2, he's standing on that point. The next step he takes beams him up to the blue piece, and he's walking down the blue piece. When he gets to positive 4, he gets beamed up to the green piece and travels along the green function forever. So the domain for this one is just all reals, isn't it? Okay. If I write that with interval notation, it would just look like that, right? Okay, what's the domain, or sorry, what's the range of this function? All the outputs. How would we describe that? How are we going to figure out what are all the possible y values an ant could stand on?
Or 1.
To 1, and do we include 1?
No.
No, we don't, do we, right? So the domain, we would just say would be something like y has to be less than negative 1, right? All those values, someplace on the function, the ant would be able to stand on every y value less than negative 1. Agreed? Okay, so if I write that as with interval notation, it would just look like that, wouldn't it? Does that make sense? Okay? All right, let's try one more of these. So how about this one? How many pieces?
3.
3. Where are our boundaries going to be between the pieces? At what x values?
0 and 6.
0 and 6. Okay. So we just end up with something kind of like that then, right? We've got our 3 pieces. The boundaries are at 0 and 6. And we've just got to graph each of the pieces in those domains. Okay, so we'll color code this again. First piece we'll call red. What are the endpoints? What's one endpoint we definitely want to use? 0, right? Because this is the line. I guess that didn't. This is the line x equals 0 is this boundary line, right? That's the right edge of the red domain. So we want to use 0. Well, what's the y value if I plug in 0 for x? Negative 3 times 0 would be 0. We see how we're getting that? We're just plugging the x value in to calculate the y value. And we're just using the equation. I think it's kind of nice to do this. Above the graph in each domain, I always just like to write what's the equation we're using. Well, that's the red piece, y equals negative 3x. What's another one we could use? Like negative 1 or negative 2, whatever. Right? Either one of those would work. If we use negative 2, 6, well, we've got 2 points. So 0, 0, open or closed endpoint for the red piece? Open, because we're not including 0, right? So we'd get Open endpoint at 0, 0. Another point on our red piece of the function is at -2, -6. And then what do we do from there? Well, we just connect those. Whoops, that's not red. We just connect those like so. There's our red piece. Good? What should our endpoints be for that middle piece? 0 and 6. What if I plug 0 into the blue equation, which is just y equals -1/2 x minus 1? If I plug 0 in for x, what do I get for my y? -1. -1 times 0 is 0, minus 1 is -1. Open or closed endpoint at 0? Closed. Yeah, because of that, right? Gives us a closed endpoint. At 0, -1. Then the other point we should pick would be, I mean, you don't have to, but it's just way more convenient. Pick 6, right? If I plug 6 in, -1/2 times 6 is what? -3 minus another one, -4. Open or closed? Open, good. Okay, so 6 -4 over 6 down 4. And then we would just connect those blue endpoints, right? And just get that. Agreed? And then finally, the green equation is just y equals x minus 7. We want to use the endpoint. So what if I plug in 6? 6 minus 7 is -1. Okay. Open or closed? Open. Yeah, open. So we get an open endpoint at 6, -1 for our green function. 6, -1. And then another point we could pick, 8 would be fine. Pick 8, plug 8 in. 8 minus 7 is 1. We get another point at 8, 1. And there's our green piece of our function. Okay, so we're about done here. What's the domain? Are there any values of x that the ant cannot stand on? 6. Yeah, look at that. There's one place where the ant can't stand that's not included in our piecewise function. So the domain, we could say, is just x cannot equal 6. Okay? The other way we could say, with interval notation, we'd have to do this. We'd have to say we include everything from -infinity up to 6 with parentheses, or everything from 6 to +infinity. But because I have parentheses at the 6, that one's not included. Make sense? Okay, we'll pick this up tomorrow. How are we doing on this? Is that making sense?
Yeah.
Okay, kinda. Okay, we need some practice.